Hello, and welcome to Alex Derives Stuff. Today, I wanted to show you a particular limit, and this limit didn't pop up out of nowhere. This is a very important limit. This limit can be used, amongst other things, to uh, prove what the derivative of x to any number is. So if you can do this limit, then you can do all of the derivatives of x to a power. Okay, so this is the limit right here. The limit as x approaches 1 of 1 minus x to the p over 1 minus x is equal to p, no matter what this p is. All right, and then what we'll end up doing in this video is I will show you that this limit is true no matter what p is, if it's any real number. If I'm really feeling it, I can probably show you that it's true for any complex number as well. But anyway, so just to get you warmed up here, to get you used to this limit, I'll at least show you some specific cases that might convince you that this identity here should hold. So I've got some special cases right here. So the first special case is p equals 0. Okay, so if I just plug in p equals 0 into that limit, then I get the limit as x approaches 1 of 1 minus x to the 0 over 1 minus x. Now, of course, x to the 0 is 1, no matter what x is. And so in this case, that numerator just becomes 0, and then we get 0 inside the parentheses, and then if we let x approach 1, we get 0. So this holds if p equals 0. Interesting. Next special case is if p equals 1. Okay, so if p equals 1, we just plug in 1 for the exponent there, and we get the limit as x approaches 1, 1 minus x over 1 minus x, right? So that whole thing reduces to 1 before we even do the limit. And if we do the limit as x approaches 1 of 1, we get 1. Okay, easy enough so far, right? So this identity is definitely true if p equals 0 and if p equals 1. Okay, p equals 2, there's a little bit more work to do. So p equals 2, the limit becomes limit as x approaches 1, 1 minus x squared over 1 minus x. And what we could do is we could cleverly like factor the numerator, right? We could say, well, 1 minus x squared, we could factor into 1 minus x times 1 plus x. Okay, and if we do that, the 1 minus x's cancel, and we're left with just the limit as x approaches 1 of 1 plus x. And if we plug in x equals 1 into that, we get 2. So if p equals 2, the limit is 2. Cool. So it holds for 0, 1, and 2. All right, I'm not going to do 3 next. I'm actually going to move around a little bit and do -1. So for p equals -1, so it's 1 minus x to the -1 over 1 minus x. So what I did to get to this next step over here is I multiplied top and bottom by x. So if I distributed the x through the numerator, 1 times x is x, and then x to the -1 times x is 1. So that's how the numerator becomes x minus 1. And I just left the x factored out on the denominator, right? And so the idea here is that the x minus 1 and the 1 minus x cancel to make a -1. So that's how we get this -1 over x here in the third step. And then in this third step, if we plug in x equals 1, we get -1. So if p equals -1, the limit is -1. Okay, so hopefully this should be pretty convincing so far. And then the last one I wanted to try was a fraction. So p equals a half. So x to the 1/2 is the same thing as square root of x, right? And I did something a little bit different here. So if you notice in these green, they've got all these z's here. So what's the deal with those? Well, what I did was I made a little substitution in this last one. So if I basically let the square root of x be the same thing as z. So if square root of x is the same thing as z, then I guess x is equal to z squared, right? So that's how the x on the denominator became a z squared. And then the important thing here is that if x approaches 1, z also approaches 1. So if x approaches 1, then z also approaches 1 because the square root of 1 is 1. Okay, so that's how the limit as x approaches 1 became the limit as z approaches 1 by making this substitution. Okay, so if that's the case, here's what happens. We do this little substitution, and we end up with 1 minus z over 1 minus z squared. And this is the reciprocal of the p equals 2 case, right? So like, because that was 1 minus x squared over 1 minus x, and here we got 1 minus z over 1 minus z squared. Okay, we got a different letter, but it's okay, whatever. It's the same. So we could write this as 1 over the limit as z approaches 1 of, the reciprocal of that, so 1 minus z squared over 1 minus z. And we already did that limit. That was our p equals 2 limit. Oh, interesting. So that gives us 1/2 here. Okay, so if p equals a half, our limit becomes a half. So hopefully, as of right now, with these specific examples, this should be convincing evidence that the original limit is true no matter what p is, right? Now, we haven't proven it, we've just shown it for those specific things, and it seems reasonable to say that this would hold for all p, but we would still have to prove that. Okay, so how do we prove that? Well, let's go back down and look at the p equals 2 case, and so see what we did right here. So for the p equals 2 case, the big thing that we had to do was factor this 1 minus x times 1 plus x. And so what that's equivalent to is using a finite geometric series. So the finite geometric series is this. If you add up 1 plus x squared plus yada 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 plus x to the n minus 1, that's the same thing as, now it's actually two things depending on what x is. If x is not equal to 1, we get this 1 minus x to the n over 1 minus x. And so this is if x is not equal to 1. Okay. If x is equal to 1, then, well, we've got 1, 2, 3, n terms. So if x is equal to 1, because you can see in this expression here, we can't plug in x equals 1. But if x is equal to 1, we can plug into the left-hand side. It's easy enough to figure out what it is. It's just 1 plus 1 plus 1 plus plus 1. And so there's n of those ones because we're counting from 0 to n minus 1. So this is n if x is equal to 1. Okay, and this is equivalent to saying that if I take 1 minus x to the n and I factor it, that's the same thing as 1 minus x times 1 plus x squared plus plus x to the n minus 1, right? So there's one view of this finite geometric series that is this, oh, is this a result of factoring this particular polynomial? Okay, and we don't need the special case where x is equal to 1 for the equivalent statement because, well, it's, yeah, so the idea is that this is true no matter what x is. So both of these things are true for all x. Okay, and so this is how you would factor this. And so this is how you take this expression on the numerator, 1 minus x to the p, and factor it, right? And then it would, and then the 1 minus x's would cancel out as long as x isn't equal to 1. And all right. Now, slight problem here. This particular statement only works if n is an integer, okay, or a positive integer for that matter, right? It works if n is 1 or 2 or 3 or 4, etc., right? Because that's sort of implicit in the counting here, right? Like oh, okay, yeah, I'm counting a positive integer number of terms here, so n has to be a positive integer. Okay. All right. So what we could do is we can adapt the little strategies and arguments that we used for those particular cases, and we can use this finite geometric series right here to sort of generalize that to all other things, right? So for positive integers, this is going to be extremely straightforward because it's sort of a literal statement of this. And if I'm going to dot all my I's and cross all my T's, basically that boils down to knowing that the left-hand side of this equation right here, this thing, is a polynomial. Polynomials are continuous, and that means that the limit is just the actual value at 1. Okay, so this limit, if p is a positive integer, so if p is a positive integer, so 1 or 2 or 3 or 4, here's what that looks like. And again, I'm going to go ahead and grab my finite geometric series thing, not the equivalent statement, this thing. So Control C, and I'll put this like over here. Maybe I'll make it purple. Okay, there we go. And so if p is a positive integer, here's what we've got. So p equals n, where n is 1 or 2 or 3 or 4, etc. Now, we've already shown that for 1 and 2, and for that matter for 0 up above, in our special cases, that this limit is true. But so the limit we want to compute, the limit as x approaches 1 of 1 minus x to the p over 1 minus x, and I'll put some parentheses around this. So that, well, okay, so for one thing, we'll replace the p with n just to be explicit about it. So this is the same thing as the limit as x approaches 1 of parentheses. So we'll make this 1 minus x to the n. So the notational difference here is just to explicitly say that, all right, the thing in the exponent is in fact a positive integer. All right, but we already know that, okay, so this is the same thing as, well, n, right? It's well, let's be more precise here. I guess we could say that this is the same thing as the limit as x approaches 1 of that 1 plus x squared plus plus x to the n minus 1. And then if we evaluate this limit, this is that same 1 plus 1 plus 1 plus 1 plus 1 n times. Okay, so then this would be equals n. So basically we get, if p equals n, our limit is n. Cool. So we've now proven that this limit holds for all positive integers. Right on. And if we look at the p equals 2 case, we can sort of see this is what we did, right? If p equals 2, this brackets here basically becomes just the 1 plus x. And that was what we did the limit of, right? If p equals 3, if we factored out a 1 minus x out of 1 minus x cubed, we'd get 1 plus x squared, and so on. Right on. All right, so that takes care of positive integers. Now, what about negative integers? Well, we can sort of follow the strategy that we used for p equals -1, where basically we just multiply top and bottom by our integer value. And we'll end up with some kind of limit where it's related to the one we already did, right? So we now know, so let's see here. So we now know that if p is a positive integer, or for that matter, if p is, I'll stick 0 in there, 0, 1, 2, 3, etc. That the limit as x approaches 1 of 1 minus x to the p over 1 minus x is in fact equal to p. Yay. So now let's do this for negative integers, right? So we can use this as a known fact, right? So we don't have to like redo all of the stuff. All right, so next thing is, well, what if p is a negative integer? Is a negative integer. So if we want to work this out, then we'll say, so p is equal to negative n, where n is a positive integer, right? So n is 1 or 2 or 3 or 4, etc. Okay, so then our original limit, so the limit as x approaches 1 of 1 minus x to the p over 1 minus x, and then again I'll put parentheses around that. That would be the same thing as the limit as x approaches 1 of 1 minus x to the negative n over 1 minus x. And then we're going to follow the same strategy that we used for x to the negative 1, right? We're just going to, so in this case, we're going to multiply top and bottom by x to the n. So we'll do this like, all right, x to the n over x to the n inside our limit. And so if we do that, this becomes the limit as x approaches 1. So if I multiply the numerator by x to the n, I get x to the n minus 1. And then the denominator, just like with the x case, I'm going to leave the x to the n times 1 minus x. Okay. There we go. All right, so what do we do with all of this stuff? All right, so one more little thing here. Now, again, we're going to use the fact that n is a positive integer here. And we're going to break this up into two things. And so we could say that this is the limit as x approaches 1. So now this x to the n minus 1 over 1 minus x, that's almost like this 1 minus x to the n over 1 minus x, except the sign is flipped on the numerator. So if we pull out a negative 1 there, we could have a first set of parentheses where we have negative 1 over x to the n. And then we could have a second set of parentheses where we have 1 minus x to the n over 1 minus x. And the whole idea here is that this second set of parentheses we know is n. This first set of parentheses gives us, all right, let's see. This first set of parentheses gives us negative 1. So we could just plug in x equals 1 for the first set of parentheses. So that gives us negative 1 there. And then this second set of parentheses right here, we know is n because we worked that out already. Okay, so we get negative 1 times n, and so we get negative n. So if p equals negative n, we get negative n. So this limit is negative n. All right. So as far as our original limit is concerned, we now know that if p is any integer, positive or negative or 0, that this identity holds. So we now know that the limit as x approaches 1 of 1 minus x to the p over 1 minus x is equal to p if p is any integer, positive or negative. All right, we're making progress here. So what comes after like knowing that this works for all integers, positive and negative? Well, we can then go to rational numbers. So fractions basically, right? Fractions of integers. And so to do that, well, let's see here. So what about if p is a rational number? And again, we're going to use the previous results. So then we want to do, so the way we could make p equal to a rational number, so we let m and n be integers, and I will assume that the n is positive. So we'll assume n is positive. So if there's a negative rational in here, that'll be included in the m. And the way we could do this is what we'll end up with is our original limit, the limit as x approaches 1 of 1 minus x to the p over 1 minus x. That becomes the limit as x approaches 1 of 1 minus x to the m over n divided by 1 minus x. And keep in mind, we know that if we have any integer, positive or negative, that this above limit in the rainbow box is true, right? Interesting. Okay, so the strategy we want to use here is similar to the strategy we used for p equals a half, right? So what did we do there? So for p equals a half, this thing, we made this little substitution where we did like, well, if I had square root of x, I'd let x be equal to z squared. And then we noted that, well, if x approached 1, then the z would also approach 1. Okay, so what's the equivalent down here where it's like x to some rational? Well, basically what we're doing is the thing we don't know is how to deal with some denominator in the exponent that's not 1. So we'd like to make a substitution that gets rid of the denominator. So if we let x, so our substitution we want to make is let x be equal to z to the n. And this is why I wanted to make, well, I guess it didn't really matter if the n was positive, now that I think about it. But if we do this, then first of all, if x approaches 1, z also approaches 1. So if x approaches 1, then z also approaches 1, because if I have 1 to any power is 1. And also, let's see here. So the whole point for this is x to the m over n. What happens to that? Well, that becomes z to the n raised to the m over n. If you remember your exponent rules, you multiply the exponents, the n's cancel, and that becomes z to the m. Interesting. So if we make this substitution here, so then we get, this becomes now the limit as z approaches 1 of, so this will be 1 minus z to the m, right? Because the x to the m over n became z to the m, and then divided by 1 over z to the n, right? Because the x was the same thing as z to the n. That was the substitution that we're making. Okay, so our original limit now becomes this limit when we have a rational exponent. Okay, so now the idea here is we want to sort of massage this so it looks like something we've already figured out. And the way we can do this is the following. We could just multiply top and bottom by 1 over z. So if we multiply this by 1, or sorry, not 1 over z, 1 minus z. So 1 minus z over 1 minus z. And we can rearrange it in the following clever way. So this limit becomes the limit as z approaches 1. So I'm going to group the 1 minus z to the m with the 1 on the denominator. So this is 1 minus z to the m over 1 minus z. And then times 1 minus z. So that's the one from the numerator. And then the 1 minus z to the n was on the denominator. Interesting. So what do we do with this? Well, check it out. Now so the assumption was m and n were both integers. And so these are limits we've done with integers, right? The 1 minus z to the m over 1 minus z, as z approaches 1. We know that that one is m. And the second one is well, it's flipped, right? It's the reciprocal of 1 minus z to the n over 1 minus z. So this becomes 1 over n. So when we multiply these, we get, in fact, when the p is m over n, our limit is m over n. And it didn't really matter whether m and n were positive or negative. I think we can assume that we have to assume that the n is not 0. So this actually makes sense in the first place, but there's our limit. Okay, so we've now proved, so we've made much more progress now. We have proved that we now know that if p is an irrational number, then, um, well, the limit that we're trying to figure out here, limit as x approaches 1 of 1 minus x to the p over 1 minus x is in fact equal to p. All right, we're getting close here. So now the tricky one here is, well, what if p is irrational? So if p was like square root of 2, so using any of our above things, what we don't know how to do as of right now is, well, what is the limit as x approaches 1 of 1 minus x to the, say, square root of 2, or over 1 minus x? So our claim here is that this would just be square root of 2, right? This is just p equals square root of 2. Or if it was 1 minus x to the pi. So how to show that, so is this in fact square root of 2? And we can't do that because the only things we proved this limit for were integers and rationals. Or I guess we could consider the integers to be a subset of the rationals, but yeah. Okay, we haven't shown that this works for irrationals, right? It seems reasonable once you've shown that it works for rationals that it would work for irrationals as well, but we don't know that for sure yet. Okay, and so to do this, this is going to seem like a bit of a hand waving here, but this has to do with the definition of real numbers. So here's the idea. So to prove this for irrationals, what we could do is the following. We could say that rational numbers form what's called a dense set along the real line, along the number line. What does that mean? It means pick a number, pick two numbers, any two numbers, and you can always find an infinite number of rational numbers in between them. Okay, so this means that between any two rationals is an infinite number of rational numbers. Okay, why is this important? Well, there's an easy way to show this, by the way. You pick two numbers that are rational. If you find the average of them, that's between them, and then so that's a number that's between them. And then you could keep doing this. You get, well, I could find the average of the middle number and the bigger number, and that's another number that's between them. And then I could keep going, and I could keep averaging numbers in the set, and I'll just get an arbitrary number of rational numbers. So that means that, like, if you have an irrational number and you want to get an upper bound and a lower bound, you can always get better bounds by, say, successive averaging. So that means that for any irrational number, for all irrational numbers, so numbers that can't be expressed as fractions, you can approximate them arbitrarily well with a sequence. So there is a sequence let's call it, so let's call these irrational numbers, I don't know. Let's call this irrational number alpha. I like alpha. So there's a sequence. So if alpha is an irrational number, or for that matter, if it's a rational number, so we could say this sequence is curly brackets, just like alpha 1, alpha 2, alpha 3, where these are all rationals that converges to the irrational number alpha. So the idea is that all of the numbers in the list are rational, and each one is successively closer to our irrational than the previous one. And and then we'll get arbitrarily close to this. Okay, and so this is in some sense, this is a loose definition of any real numbers, like by some sequence like this. Now, typically, for the purposes of our argument, we know that well, we know that this will work. Okay, so for the purposes of our argument, we don't need to explicitly find one of these things, but we already know that, well, for all of these rational numbers, well, we know that the limit as x approaches 1 of 1 minus x to the alpha 1 over 1 minus x, well, that's just alpha 1 because alpha 1 is rational. And we could do the same thing as for this, the limit as x approaches 1 of 1 minus alpha 2, the second number in the list, over 1 minus x that's the second number in the list, alpha 2, and so on and so on and so on. And if we let the subscripts approach infinity, so the limit as x approaches 1, I got to think about this for a second. This is like a double limit right here, right? So we'll do the limit as k approaches infinity of the limit as x approaches 1 of 1 minus x to the kth number in the list. Okay, so this inside limit here, that just approaches alpha k, which is assumed to be rational, right? So this is equal to the limit as k approaches infinity of alpha k, and then that is the same thing as just our irrational alpha. So if alpha is irrational, then there's a sequence of rational things that approximate it. Okay, and all right, this was very technical looking right here, but the basic idea is this, is that if I want to raise x to an irrational power, what I could do is I could find a rational approximation to that irrational power and do x to that. And if my approximation to the alpha is good, then my approximation to x raised to that alpha will also be good. So that's it. So then, yeah, so long story short, the limit, so if alpha is irrational, so if p is irrational, then the limit as x approaches 1 of 1 minus x to the p over 1 minus x is still p because of this sort of denseness property of rational numbers on the number line. And so we've got irrational numbers and rational numbers. Put those together, that's all the real numbers. And there we go. So this limit is true no matter what that exponent p is. All right, so as a follow-up to this, next time I can show you how to use this limit to prove all of those derivative rules for x to the something that you learned, and basically knowing this limit will immediately get you a whole lot of your famous results from calculus. So I hope everybody enjoyed that, and I'll see you next time.